Okay, so this is question 2, and it's part B of the question. It says that what happens here, I'll just quickly read off the instructions. They fill in burette with 0.02 mole per dm cube of potassium manganate. So I assume that's titration happening. They measure out 25 centimeter cube of Fe2 plus Fe3 plus solution using a measuring cylinder. Now, before I read the questions, I was already questioning the instructions. Why are we using measuring cylinder and not some accurate apa ni? What do we call them? Apparatus, yeah. Like measuring cylinder is, yes, great, but it's not accurate. There's pipette. Pipette is more accurate. Burette is also more accurate. And another thing is volumetric flask. Okay, the volumetric flask di sana, the one with that faint line, with the long narrow, that is considered more accurate, definitely more accurate than measuring cylinder or beaker. Okay, and then they add sulfuric acid, that's just to acidify the reaction. Then they do titration. Okay, set A. Set B, same thing. The only difference is they add zinc. The volume is also different. They add zinc so that the Fe3 plus is being reduced to Fe2 plus. I don't know if you still remember the information that zinc reduces Fe3 plus to Fe2 plus. Okay. So the first question, identify an experimental weakness in step 2. Explain how this would affect the results. So you can already see in step 2, I was already questioning that the weakness is they used measuring cylinder, measuring cylinder was used to measure out the solution, the result. Pulang. So what's the problem with using measuring cylinder? It's not accurate, and this can result in inconsistent titer values. Okay? How could this weakness be overcome? So how can we solve this problem? What can we use? Use pipette or volumetric flask. Okay, yep, that's fine. Use pipette to measure out the solution. They also accept or volumetric flask. Okay, and then they have okay, so they have the results, the titer values for set A and set B. I assume that you were able to work out the titer volumes. They say complete both tables and calculate an appropriate average titer for each set of results. The student could not carry out titration 3 in set B. Record the average titer to 1 decimal place. Okay, so let's start with set A first. Rough titers must never be included in your average. I hope you all know that. Okay. Before I move on, what's the maximum difference between two titers values are you allowed in the practical? 0.2 or 0.1? 0.2? The difference between two titers must be within 0.1. So they must be 0.1 within each other, okay? So, do you see titration 1 and titration 3 are within 0.1 0 centimeter cube to each other. So we will only take the average of titration 1 and 3. Automatically, titration 2 will not be included in our calculation. Okay? So only 1 and 3 as they are within 0.10 centimeter cube difference. Okay? So if you take the average, 17.10 plus 17.05 divided by 2, you should get 17.075. And we want to one decimal place. Yes. So to one decimal place is 17.1 only. Okay? That's set A. For set B, you only have two titers. You have no choice. Okay? And you cannot use only one. Titration, titer value must be an average of at least two numbers. Okay? So you would just take the average of 43.45 plus 43.60 divide by 2. Even though they are not within 0.10 centimeter cube difference. 43.5 plus 43.60 divided by 2. 43.5, did you get that? Okay, good. Next, this is the calculation. This is the scary part, okay? So I am going to use a fresh page because I know I will need a lot of space to write this down, okay? So I'll read the question. As I read the question, I will also draw the diagram. We were supplied with 250 centimeter cube of Fe2 plus Fe3 plus, correct? Original, original solution, original amount of Fe2 plus and Fe3 plus is on page number 4 if you're looking for that information. This is made up of Fe2 plus and Fe3 plus. Okay. Back to page number 5. Fill a burette using a measuring cylinder. Transfer 25 centimeter cube of Fe2 plus, Fe3 plus into a conical flask. Okay, so I take, this is my set A. I take only 25 centimeter cube of that. Still Fe2 plus, Fe3 plus. And I titrate it with potassium manganate. Yeah? The potassium manganate has a concentration of 0.0200 mole per dm cube, KMnO4. What is the titer value of set A? Berapa tadi titer value of set A? 17.1. Volume of potassium manganate was 17.1 centimeter cube. Okay? Okay, I'll leave it at that. I do the titration. So you can see that if I know the volume and the concentration, I can find the number of moles of potassium manganate. Okay? But I'll leave the calculation for later. The second experiment, which is called set B, I take 100 centimeter cube from the original solution. And this is Fe2 plus and Fe3 plus. Okay? Next, I add zinc. Now, what does the zinc do? the zinc will reduce whatever Fe3 plus I have here into Fe2 plus. So, zinc will reduce Fe3 plus to Fe2 plus, and I want to call this Fe2 plus reduced, Fe2 plus red. That means it has been reduced, all right? So then they filter filter the mixture into a beaker. Okay, so now I have some filtrate, still 100 centimeter cube. However, this time, what is inside the beaker? I have Fe2 plus originally, just now from here. I call that Fe2 plus ori, and the Fe2 plus that was reduced by the zinc just now. Fe2 plus reduce. Can you see, can you understand this part? Okay, I repeat. When I take 100 centimeter cube of the Fe2 plus Fe3 plus solution, I add zinc. And it mentions that allow time for reduction of Fe2 plus to take place. So that means this zinc will reduce all my Fe3 plus here into the new Fe2 plus, which is what I call Fe2 plus reduced. And the original Fe2 plus in the solution, I will call it the ori Fe2 plus. Okay? So, inside this beaker, all of them are Fe2 plus. There's no more Fe3 plus left. However, I know that this Fe2 plus reduced came from Fe3 plus. Okay, so that's the only difference. Next, transfer 25 centimeter cube. Okay, so that means I take only 25 centimeter cube of my Fe2 plus ori, Fe2 plus red solution. 25 centimeter cube, and this contains Fe2 plus ori, Fe2 plus reduce. You may ask me, why don't I just call it Fe2 plus straight away? Because this Fe2 plus reduced comes from Fe3 plus, and I want that information about Fe3 plus. Okay? The difference between these two titration is that this contains all Fe2 plus. This one contains just the original Fe2 plus. Fe3 plus will not get involved in a reaction with potassium manganate. Same thing, I do titration with potassium manganate, same concentration, 0.02 mole per dm cube of potassium manganate. And what's the titer value for the second part, set B? Berapa tadi? 43.5 cm cube. Okay? Right. Reading the question. Okay, I'll let you copy this down first. Do you need time to copy this? So the question says, calculate the mass of Fe2 plus ions in 100 centimeter cube of the reduced solution produced in step 6. So that means in set B. Step 6 is set B, right? So part 2 is actually interested in our set B reaction. So calculate the mass. I don't know anything about Fe2 plus. Now, bear in mind, both Fe2 plus ori and Fe2 plus reduced will react with the potassium manganate, okay, because they are Fe2 plus, so they all will react. But I don't know anything about Fe2 plus or Fe3 plus. However, I do know the concentration and the volume of potassium manganate required to react with this system. So what I can do is find the number of moles of manganate. I will just call it MnO4 minus. So that's 0.02 times 43.5 over 1,000. Is it 8.7 times 10 to the power of minus 4 mole? Okay, that's manganate. I want to know the number of moles of Fe2 plus, both ori and reduce. How do I find the number of moles of Fe2 plus? Mole ratio, good. It is 5 times number of moles of manganate ion. Yeah? So times 5, 4.35 times 10 to the power of minus 3 mole. But the question wants mass. Mass of Fe2 plus, again, both ori and reduce, is number of moles times MR or AR in this case. Okay? So 4.35 times 10 to the power of minus 3 times 55.8, which is, lurus ka to? Minus 3 times 55.8. Did you get 0.243 grams? Not the final answer yet. 0.243 grams for this part, okay? Now remember, this mass is only for volume 25 centimeter cube. So the mass in 25 centimeter cube is 0.243 grams. If you read the question, they want the mass in which volume? 100. So that means they want this, the mass in this beaker, which is related because you took 25 centimeter cube out of that beaker, right? So if you have in 25 centimeter cube, the mass of Fe2 plus ori reduced is 0.243 grams. What is the mass of Fe2 plus ori in reduced in 100 centimeter cube? So you just cross multiply them. So 0.243 times 100 divided by 25. So the mass of Fe2 plus ori and reduced in 100 centimeter cube is 0.972 grams. Do you all agree? And that is your answer for part 2. Okay, so now I can fill in the information. I know there's 0.972 grams here. And if I go back here, there's also 0.972 grams. Now, do you agree that the mass of Fe2 plus and Fe3 plus is 0.972 grams in 100 centimeter cube? Okay, good. That's part 2, the answer to part 2 of your question. For 2 marks, How many minutes have we spent? I know I go really slow because I draw the diagram for you. Okay. Next is part 3. Calculate the mass of Fe2 plus ions in the original solution using the appropriate average titer from 2D part 1. Okay, so that's macam vague sikit lah the question. Like, what do you mean by Fe2 plus ions in the original solution? Okay, so you see here, set A. I took 25 centimeter cube of that solution, and that I reacted it with potassium manganate. Okay, so between Fe2 plus and Fe3 plus, only Fe2 plus will react with the potassium manganate. Fe3 plus will stay unchanged. Okay, so if I know the number of moles of Fe2 plus here in 25 centimeter cube, I can trace back and find out the number of moles of Fe2 plus in 250 centimeter cube. Okay, so let's do that. The same method like we did for set B. Okay, we always start with concentration, volume. So from there, I can find the number of moles of manganate ion, 0.02 times 17.1 over 1000, which is 3.42 times 10 to the power of minus 4 mole. But I'm not interested in manganate. I'm interested in the Fe2 plus. Number of moles of Fe2 plus is, how do I find the number of moles of Fe2 plus? Mole ratio again, 5 times number of moles of manganate, which is times 5, 1.71 times 10 to the power of minus 3 mole. The question wants mass. So I have to times it by the MR, or AR in this case, 55.8, and I should get 0.0954 grams. And this is the mass in 25 centimeter cube. But what does the question want? In 250. So I go back to the original solution. That means in 25 centimeter cube, there's 0.0954 grams. What is the mass in 250 centimeter cube? So times 250 divided by 25. So the mass of Fe2 plus only is 0.954 grams in 250 centimeter cube. So I can add this information now. Okay, I know that in here I have 0.954 grams of Fe2 plus. Okay, and that's the answer to part 3. It's not 0.0954, but you have to multiply it by 10 because they want the total mass in the original solution, in the original volume, which is 250. Okay, next, I want to find the percentage by mass of Fe3 plus. I don't know anything about the mass of Fe3 plus, okay? But I know mass of Fe2 plus alone, and I also know the mass of Fe2 plus Fe3 plus, however, in 100 centimeter cube. So this 0.972 grams is the total mass of Fe2 plus and Fe3 plus in 100. I want to know the total mass in 250 centimeter cube. So I need to go back, I need to trace it back again. Okay, so that's part 4. Maybe see it. Okay, part 4 of the question. I know that mass of Fe2 plus, Fe3 plus in 100 centimeter cube is 0.972 grams. What is the mass in 250 centimeter cube? So 250 times 0.972 divided by 100, I have 2.43 grams. Okay? So then I can add on to my diagram. In the original solution, I have 2.43 grams of Fe2 plus and Fe3 plus. Do you think I can find the mass of just Fe3 plus alone? Yes. How? Minus, okay? So that means I will answer the percentage by mass of Fe3 plus. I need mass of Fe3 plus over the total mass of the whole solution times by 100. Okay, so to find the mass of Fe3 plus, I need to take 2.43 minus 0.954. Do you all agree? Yes. Okay. 2.43 minus 0.954. The total mass is for both ions, Fe2 plus, Fe3 plus. That means it's 2.43 grams. And that is how you solve a 4-mark question. To me, it's just not worth it. Okay? But I need to teach you so that if it comes out, you cannot say that I never taught you this calculation. Yeah, it's not easy. It looks easy because it's just 1 mark, but nope. State what change could be made to the procedure to enable titration 3 to be carried out in set B. Okay. Mana set B tadi? Set B is that okay, so you saw that in set B, the titer values are very big, right? 40 something, 40 plus. And usually titer value, titer values are within like 20, 30, 25, right? So what can you do so that we don't have to use a big amount? Okay? Okay, so everything is fixed. Number of moles of manganate is 8.7 times 10 to the power of minus 4. Number of moles of Fe2 plus is 4.35 times 10 to the power of minus 3. If you want to reduce the number of the volume of potassium manganate being used, you need to increase the volume of Fe2 plus, Fe3 plus. Okay? So how does that work? We cannot change the concentration, but we want to increase the number of moles, right? We increase the number of moles, so What change could be made to the procedure to enable titration 3 to be carried out? Instead of using 100 centimeter cube of Fe2 plus Fe3 plus, we increase it even more. Okay? Supaya you have big number of moles of Fe2 plus, you just need small amount of manganate. Okay? So use bigger volume of Fe2 plus, Fe3 plus, bigger than 100 centimeter cube. I know that's already a lot. To increase the number of moles so that less manganate ion will be used. Okay. Okay. I personally don't like question 2. And I think that should be it for today. We will continue with carboxylic acid theory tomorrow.